Alright, so now that we understand what a definite integral is and how it's related to area, we have an idea of how to use the Riemann sums to approximate both definite integrals and area, as well as using some geometric area formulas to calculate these areas and definite integrals. What we're going to do is we're going to look at some examples, some things that are going to start to look like some of the questions that we might see in the free response section especially. Like for example here in example 8, you're going to be given that you have f of x is a continuous function, and you're given that it's a continuous function where the function itself is greater than or equal to 0 for all x. And so that's going to be important because if you think about the section that we're in, they're going to ask you here to approximate a definite integral, and then they ask whether or not this represents the area. So based on the information that you've been given so far, hopefully your answer to this, does this represent the area, the answer is going to be yes. And we'll just make sure that we definitely answer it before we kind of walk away from this. The other thing I want to highlight here, just to kind of always pay attention to when you read your free response, you're given that f of x is a continuous function. And since f of x is here, okay, and this is kind of where free response starts to be fun in calculus, because not only are we going to be doing integrals and working backwards, we'll consider this to be part A, where we approximate this. B is going to be our, does this represent the area? But notice they've given you a part C here, and they want you to approximate the derivative of f at 1 using the values in the table. So let's talk about what we know based on the fact that they've told us that f is a continuous function. All right, from chapter 5, what we know is that if this is f of x is representing a derivative, that because it's continuous, the derivative is continuous, then we know that we can find an antiderivative, that we're going to be able to integrate. So this function is integrable. Now we also know that this is chapter 5, but we also know from the fact that it's a continuous function from chapter 3 that any function that is continuous, as long as we have no cusp or unusual steepness, then we are going to be able to estimate a derivative. So they're asking us to approximate f prime of 1. So we're going to assume that f prime of 1 exists, there's not a cusp there, and so we're going to use values in the table to help us approximate that. Okay? And so what we're going to do is, let's start with the A. Let's start with our approximation of the definite integral. So we label it, because that's always important. What are we going to do? And then we are approximating, so we put our approximation. Now it just says using numeric methods. That basically means use a Riemann sum. We'll go ahead and we're going to practice them all. They'll be very specific on the AP. They'll say do a left Riemann sum, do a right Riemann sum, do a trap sum. They'll tell you what they want. So I'm going to go ahead just for practice. We're going to do a left, a right, the midpoint, and the trap, just like we were doing before. Now, unfortunately, you're not going to be able to do these on using the summation notation because you don't have an actual function, you're just having the value. So we're going to plug and chug on this one with our calculator. So the first thing that I would do is you got to decide what n is. How many rectangles are we going to have? So on this, you're kind of scanning through here. I noticed that my x's are all equidistant. So one option would be if I wanted to do the left, the right, and just a trap and not worry about midpoint, I could do 6. So let's kind of put this down as options. You can do n equals 6 and do L6, R6, and can't do M6, and T6. Or we could do n equal to 3, because if I do 3, notice that very nicely they gave me a midpoint of 0 and 1, a midpoint of 1 and 2, and a midpoint of 2 and 3. And mostly because I don't want to write 6 sums, I'm going to do the n equal to 3, and I'm going to do your L3, your R3, your M3, and your T3 as my estimates, okay, since it doesn't really specifically say. So I'm going to calculate my delta x, given that I'm using 3. My interval is 0 to 3, so we have our f of x that we're calculating on our interval 0 to 3. And so that is going to be 3 minus 0 divided by 3, which gives us a very nice delta x of 1. So let's do our R3 first. So 1 times, now I get my heights. Now they don't really care if you come in here and you say f of 1 plus f of 2 plus f of 3 when they're doing it. Or instead of writing f of 1, you could actually just put in its place what f of 1 is, which is 6 plus f of 2, 4 plus f of 3, 5. They don't really care if you do this line or this line. They'll understand what you mean either one. So you choose whether you want to do f of and then just go get the numbers. And then this is nice enough. We're just going to add it up and we'll get an estimate of 15. Then I'm going to approximate with L3. So that would be 1, and on that one it would be f of 0, f of 1, and f of 2. So I can go get those values. And again, it's not necessary to write both of these. I'm just doing it for your benefit. So I would take 2 plus 6 plus my 4, which is going to give me 12. Okay. And then we'll do our midpoint, M3. Again, my delta x is 1, and I'm using f of 0.5, f of 1.5, and f of 2.5 in my calculations for that one. And again, just to write it so you know where I'm getting my numbers from, I would use my 4 plus my 7 plus my 1. So that's going to give me 12 for M3. And then I could approximate with T4, which would simply be your right plus your left divided by 2, 27 over 2, which is 13.5. Okay, so it's not too bad. Usually when you see these and they're on a non-calculator section, it ends up being something that you can plug and chug fairly quickly. Now notice they did not ask in this problem whether the left and the right were over or under estimates. And they're not asking you that because they never gave me any information about the function being increasing or decreasing. So that's pretty much it, and so we would have our approximation by one of these methods. All right, and does this represent the area? The answer for B is yes, because f of x is greater than or equal to 0, the integral from 0 to 3 of f of x dx does represent area because they're both positive. The definite integral is positive and the area is positive. Alright, now for part C, this is because, in the AP, they don't just in isolation ask you chapter 5 material, they'll ask you chapter 5 and chapter 3 material. So they've asked me to approximate f prime of 1. And to find an instantaneous rate of change, I use an average rate of change. I could use the symmetric difference quotient and use the secant line on either side of 1. So what would probably be best in this situation is to come in and use our 0.5 and our 1.5. So you remember you have to show your difference quotient. So the instantaneous can be approximated with the average. And the average would be your f of 1.5 minus f of 0.5 all over 1.5 minus 0.5. So then you could just go ahead and do your calculations. 7 minus 4 over 1 or 3. Okay, and so that would be what they're looking for in a problem like this, which is fairly straightforward as long as you're paying attention to what exactly they're asking us. So this is where you're doing approximations. Notice I have approximated an integral and I have approximated a derivative. So they're going to work you both ways and ask and make sure you know how to do approximations. All right, now for example 9, the reason why we put this one in is because I've been saying all along that you do not have to have your delta x be equal with subintervals, which is what we've been doing kind of up until this point. So when we're doing approximations with Riemann sums, there is no requirement that your delta x, your rectangles, have the same width for every rectangle. No requirement. So when we are doing this approximation, so it's the same kind of idea. I'm going to approximate. I have a continuous function, so I know that f is integrable. That does not you can integrate, and the spelling that I have is sometimes fairly terrible. There we go. So you can take it, you can integrate it, and you can, oh actually we don't know if we can differentiate or not. We'll assume that since they're asking me to approximate at that value, I can. Remember, because if it's continuous, it may or may not be differentiable. All right, so we're going to approximate. So let's first do the 1 to 8 of f of x dx. And then let's decide on our approximation. Since these are all, there's no way you're going to do midpoint, so you might as well just throw that out. So let's do a left and a right. And for these, our n is going to equal, just basically count up how many you have. This would be for your first rectangle. This would be for your second rectangle, your third, your fourth, and then your fifth and your sixth. So we're going to do an R6, I'm going to do an L6, and I'm going to do a T6. I'm going to throw the midpoint out because that's not going to help me. Now what I want to be careful of in this problem is that your delta x, for the first rectangle, delta x is equal to 1. But for the second one, delta x is 2. For the third one, delta x is 3. Then we get delta x is 0.6. And delta x equals 8 minus 6.6, 1.4. And the last one, delta x is 2. So we notice that we have different widths of our rectangles, but that's okay. We're just estimating anyway. So when we do our Riemann sum, we just have to remember we're going to have to do f times f of the right endpoint of the first one, which would be 1, plus 2 times the right endpoint of the second rectangle, which would be 3, plus 3 times the right endpoint of the third one, which would be 6. And then we have 0.6 times f of 6.6. And then 1.4 times f of 8. Plus 2 times f of 10. I should have wrote smaller. And so the actual calculation we're going to be doing is basically 1 times f of 1, which is 3, so 1 times 3, plus 2 times f of 3, 3, plus 3 times f of 6, 1, 0.6 times f of 6.6, which is 5, 1.4 times f of 8, which is 8, and then 2 times f of 10, which is 10. And then we basically add all this up and combine it together. So we would have 3 plus 6 is 9, plus 3 is 12, plus another 3 is 15. So I'm at 15 right here. And then I have 1.4 times 8, so that would be plus 8 plus 3.2. And then I have 2 times 10 plus 20, so we're at 35, 43, 46.2, 46.2. So even if you were on a non-calculator section, you should be able to do something like this. Now again, remember they don't care whether you write the first line or the second line. So if you want to, like when you go to do this L6 approximation, I might go ahead and I kind of do 1 times 2 times, put my delta x's in. And then I just go in and fill in what I need using the left endpoint. So I would have to use the f of 0, which is 4, and then 3, and 3, 1, 5, and 8. And then go ahead and add those up. So we have 4 plus 6, 10, 19, 19.6, 24.6, 26.6, and 2 times that, 16. So I end up with 42.6 for that one. And then of course my trap sum, if I'm estimating with that, is going to be 46.2 plus 42.6 and all over 2. Now I think I might need to re-add these up just to make sure I have them correct. So I'm going to pause and just check my math real quick. Shockingly, I managed to add correctly there. We know I have problems with that in class. So, and then we just average these two together. So you end up with 88.8 divided by 2, or 44.4. So those are our estimations using the numerical methods for this definite integral. Now, again, the second question is, does this definite integral represent the area? Now, you be very careful about this. You're going to be tempted to say yes because all of the function values that we are using were positive. However, we were not given that f of x greater than or equal to 0. So the definite integral 1 to 8 of f of x dx may not represent area. And by area we mean the total area, because we don't know if it went below or above, so we can't be 100% sure that this actually is the area, that they are the same. All right, and then our last one, we want to approximate f prime of 7. All right, so we're going to approximate that. Now you're like, wait a minute, they didn't give me 7. And I'm like, well, okay, that's fine. They didn't even give me equidistant ones. That's fine. Pick the points that would be closest to where 7 is and just do basically a symmetric-ish difference quotient. So we would have our approximation for the instantaneous rate. We would do f of 8 minus f of 6.6 divided by 8 minus 6.6. And so basically we would get our f of 8, 8 minus 5 divided by our 1.4, 3 over 1.4, which is 2 and something. Approximate, it's probably fine just to leave it like that. If you don't want to have the 1.4 on the bottom, you don't have to simplify, but you could go, hey, it's 30 over 14 and have a nicer fraction. So we'll leave that there. So that's an example on this page of 2 examples where we are doing numeric approximations using tables that they have given you in your free response questions. All right, now what we're going to do in example 10 is, notice it says we want to sketch the region and then we want to evaluate each integral using a geometric formula. That instead of approximating, we are going to find the exact value. Okay, I'm going to stress that. The exact value, but remember we don't have any of the shortcuts yet for calculating definite integrals. And I definitely do not want to do the limit definition and do that long thing like you had in number 55. So I am going to hope that when I sketch these, that it's either going to be a triangle, a trapezoid, a rectangle, a square, or a semicircle. Since these are functions, you can't have a full circle, but you could have part of a circle that we're going to look at. So I look at this and I say, all right, I'm going to sketch a real quick sketch of y equal to 4. And y equal to 4 is nothing more than a horizontal line. And I am interested in the bounds 1 to 3. So we're looking 1 to 3. And so the area that we are looking for is nothing more than a nice little rectangle. It has a base of 2 and a height of 4, and we are done with the problem and walking away. The answer is 8. Okay. For this one, it doesn't bother me. This is still a linear function inside, so I'm going to graph y equals x minus 2, which has a y-intercept of -2 and a slope of 1. Right, and we're going 0 to 3. It's also important to know that that's an intercept there. So here's my 3. So the area that I am going to be looking for on this function is I'm going 1, or actually 0, which is this portion, to 3, which is that. Now, is this going to be total area? This one happened to be total area. This one, remember that the definite integral is the accumulation of area. So it is not going to simply be find this area and find this area. You need to remember that this portion is actually going to be negative and this portion is actually going to be positive, and we're looking for our net. Okay, so remember that we're doing the net area here, not the total area. So I would first calculate the area of this piece, which is nothing more. You have a base of 2 and a height of 2, so it's 1/2 base times height. So the area is going to be 2. And this area over here, 1/2 my base times my height. If I plug in 3, I only went up another 1 because your slope was 1, so 1. So your area here is 1/2. But now remember that the definite integral is your net. So the definite integral coming across here would be a -2, then plus the 1/2. So the definite integral, the net that you have, would be -1.5. All right, now let's take a look at example C here, which we have the square root of 36 minus x squared. And you should basically y equals square root of 36 minus x squared. Realize that because this is plus, that this is the top half of a circle. Okay, if I square both sides and then move the x squared over, it's x squared plus y squared equals 36. So it's a circle centered at the origin with a radius of 6. And because it's the plus square root version of that, we know that we're doing the top half. And so this also would be 6. And so if I was calculating the area of this, the area of a circle is pi r squared, but it's only half the circle, so the area would be 1/2 of pi r squared. My radius is 6, so it's 1/2 of 36 pi, or 18 pi. So the area is 36 pi. And then this definite integral that I'm looking at, then I am trying to calculate the definite integral. Well, the definite integral and the area are exactly the same thing. Oh, it's 36 pi times 1/2, which is going to give me 18 pi. So the area, the functions above, hence the definite integral and the area are the same thing. So my answer is 18 pi. All right, taking a look over here, we have our signum function this time. And so we're calculating our area, so let's sketch our picture. the signum function, if you will recall, is 1 if x is positive, -1 if x is negative, and it's undefined when x is 0. And I'm trying to find the area in between the function and the curve. Well, this is the definite integral, my accumulations from -1. So that's this, or actually losing to start with, and then I'm gaining up until I get to 4. Now you might be a little concerned about the fact that there's a discontinuity right here in the middle of this, but guess what? It does not bother us at all. That this is a derivative of something that we actually can integrate. And if you think about it, it's y equals absolute value of x, because the slope for the absolute value of x is -1 on this side and 1 on this side. And that's what this function is giving us. The slope for the negative values is 1, the slope for the positive values is 1. So this is an example of where we have a discontinuous f of x that we can integrate. So the fact that this is discontinuous does not mean that I can't integrate it. Okay, that it all depends. Remember, that's that gray area. But when you look at your picture, you're like, oh, okay, I am just accumulating my area. I'm going to take this area out. So I first calculate what it is. It has a width of 1 and a height of 1, so that area is 1. This area has a width of 4 and a height of 1, or 4. So I took away 1. And then I add the 4 back in for my accumulation, which gives me 3, and then we're done with that problem. So this is what we call an idea of don't worry if this is discontinuous, because being discontinuous does not mean that I can't integrate. I may or may not be able to integrate. And in example 10, the big idea here is if you can use geometry, then use it in order to calculate the definite integrals. That's one of our shortcuts for calculating these definite integrals. We're going to come up with some fancier shortcuts than that, but we always check to see if we have some geometry we can use. All right, so here's another example that you might see. Instead of them giving me formulas, they're going to give me a picture. And then notice they tell me I have line segments and I have a semicircle. So right there you know that you can calculate each of these areas. This area, you have 1, 2, 3, 4, 5, is going to be 1/2 of 5 times 1, or 2.5. This area is going to be 1/2 of pi r squared. And so since the radius here is 2, so this would equal 4 pi times 1/2, or 2 pi. The area here, now we probably should figure out what this actually is. This kind of thing, you don't always assume. I'm pretty sure it's 1/2, but let's think about the slope here and make sure that it would work out. The equation of this line would be y equals my slope, -1 minus 3 over 5 minus 3, -4 over 2, or -2. So -2, and let's do x minus 3 plus 3 for the equation, and be like, hey, that would equal 0. Just verifying for myself. Subtract 3, divide by 2, so that would give me -3 over -2, 1.5 equals x minus 3, x equals 4.5. All right, so we have verified that that value is 4.5. So this is 1 2.5, so it's 1/2 of 2.5, 5/2, times the height, which is 3. So my area here would end up being 15/4. And then one last one right here. Okay, this area has a 1/2, base of 1/2, and a height of 1. or 1/4. So I can calculate all of these areas by nice geometric formulas. Now, what they've asked me to do here, and this is all pre-work, and the nice thing about the AP is if they gave you this graph and you wrote this information up here on the graph, they will use that, they will read the graph and realize where you're getting. You don't have to redo the work that you have up here on the graph. So they're asking me to evaluate the integral from -7 to 0 first. From -7 to 0 of f of x dx. So I'm going from -7 to 0, and this is the definite integral. So we know that we're going to lose area first. So we're going to lose the 2.5 area. And then we're going to gain 1/4 of the area that we have here. So we would gain the pi. So then we're done. We have our answer. If I look at the second part, it's asking me to calculate 2 to 5. So for b, the integral from 2 to 5 of f of x dx is between, here's my 2 to 5. Well, that's exactly this area of the triangle. So it's going to be the 15/4. And then the last question that they're asking me is, do these integrals represent the area? The answer is this one is net area, not total area. The reason that this one was only net area and not total area is because you had a negative portion of the graph. This one right here is total area because our function was positive for the entire interval 2. Oh, you know, I need to say no. You know what I forgot to do there? I just looked at that nice little mistake I made. Let's come back and erase this. It's not going to be total area because if I'm supposed to go all the way to 5, I need to take the 15/4 that I had, and then I need to take away the 1/4, so I get 14/4 or 7/2. So the answer actually is no, both of these are net area, not total area. Okay. And then they say, well, what is the area of each region? All right, so let's kind of put this down at C. So the area between f of x and the x-axis from -7 to 0 is going to equal 2.5 plus pi. Notice I didn't label this with an integral. Because they were not the same, I cannot label them the same. I have to label them separately. And the area between f of x and the x-axis from 2 to 5 is going to be 15/4 plus 1/4, which is 16/4 or 4. And so that's kind of the idea that we're looking at, knowing how we're calculating our definite integrals versus how we're calculating our total area. All right, I'm going to stop this video here and pick up the next one to talk about some properties of definite integrals.